Hey everyone, I'm Vineeth. I'm a PhD student at University of Delaware, and I'm advised by Dr. Sunitha Chandrasekharan, and I'm part of the Computational Research and Programming Lab there. So today I'll be talking about a workflow called in-transit machine learning using PyTorch on Frontier Exascale system. This is a use case of PyTorch for a scientific application running at scale. So this was a collaborative effort across the US and Europe. So this includes University of Delaware, Oak Ridge National Lab, and HCDR, which is a national lab in Germany. So to give a background about the science case, Pick-on GPU simulation is a particle-in-cell simulations, physics simulation that tracks particles within a grid representing the space. I'm a computer scientist, and the benefits of working with an interdisciplinary project is that we get cool graphics. So I'll show you cool graphics. So here you see a laser pulsing through a plasma channel, and the pulse displaces electrons in the channel, creating a wake, thus creating positive and negative charged regions, which is accelerating the electrons to achieve higher and higher energies, thus creating a high energy particle accelerator which is the goal of this project. So we want fast and predictive simulations for the next generation laser plasma accelerators. So I want you to imagine that you're looking at the Golden Gate and there's a ship going underneath it, forming waves due to the water it displaces. Now imagine surfers jumping into the wave and riding the wave. They get accelerated, don't they? In this analogy, the San Francisco Bay is the plasma channel, the ship is a laser pulse, and the waves are the radiation, and the surfers are the individual particles. So what's the point of these simulations? These simulations have various applications like chemotherapy, where concentrated energy needs to be maximized while reducing its effect on the surrounding regions and particles. So the challenge with all of these simulations is that they require solving complex nonlinear equations for trillions of particles, creating terabytes of data. And the use of machine learning allows us to learn complex dynamics from this data. So going beyond just our application, the use of machine learning to learn from large volumes of simulation data is not a unique problem to Pick-on GPU. A couple more examples are that digital twins, such as Destination Earth from the European Commission, uses climate and weather models such as ESMs and ECMWF's IFS, both of which generate large amounts of data. And there's also the CERN's Large Hadron Collider, which is a particle accelerator that we're all familiar with. So where do we run all of this, right? We run this on the Frontier Exascale system. This is currently the fastest supercomputer. It's located at the Oak Ridge National Lab, and it contains approximately 37,000 total AMD MI250X GPUs. And Pick-on GPU was one of the 8 research projects that was selected in 2019 across the country to test the system. So to give an overview about the architecture of a single node on Frontier, so this has, again, the AMD MI250X GPUs, so it technically has 4 GPUs, but what you see on the right is it's logically presented as 8. That's because the software sees AMD's MI250X GPUs as 8 individual GPUs because of the way the architecture shows up. So each GPU contains 2 graphic compute dies, so high-level libraries like PyTorch see 2 GPUs. And Pick-on GPU's PyTorch code was single GPU for NVIDIA GPUs. My role was to test and validate the PyTorch GDP scaling on the AMD MI250X GPUs on Frontier. When we first started, it wasn't clear to what extent PyTorch would scale, especially on AMD GPUs. So the challenge is that as GPU acceleration of plasma simulation codes, such as Pick-on GPU, advanced and led to a speed up of the data generated, The volume of the data stream produced by the simulation made offline analysis of such simulations impossible due to file system and I/O constraints. This is because the GPU acceleration led to the increase in data generated. So there is a mismatch between throughput of the GPU memory and the file system throughput. So the solution is to use in-transit training of complex ML models which require processing of data produced at source by the simulation at extreme data rates through streaming. The data is streamed from the simulation using to PyTorch using a custom implementation of OpenPMD, which stands for Particle Mesh Data Standard. And the combination of OpenPMD API and Audios 2 allowed direct in-memory transport between one parallel producer code to an arbitrary number of parallel consumer codes, which in our case was the PyTorch code. And the data streams are established only between the processes that share data, reducing communication bottlenecks. So why do we need streaming? This is mainly because of system constraints we face. So 20 to 30 terabits per second of parallel throughput is produced by the simulation versus the file system, which only has about 10 terabits per second of bandwidth. And just to give an example, when scaling to just 25% of frontier system, so approximately 37,000 divided by 4 is about 9,000 GPUs, 1 petabyte of data is produced for every time step. And in our simulation, there's approximately 1,000 time steps where each one lasts from 0.1 seconds to a second. So we often see 1 to 10 petabytes per second of particle data requiring on the order of 10 exabytes of total disk space. So the upshot here is that the storage can basically be exhausted in as little as 100 seconds. So this is why the in-transit ML is necessary. And to give you an overview of the idea of what's going on here, we use in-transit ML to bypass disk storage, which is a bottleneck for applications like pick on GPU. The simulation produces so much data that we must still do reduction before the ML model can reconstruct and learn correlations, reconstruct the data and learn correlations. In our case, we do intra-node streaming, where the simulation, which is the producer, and PyTorch, which is the distributed consumer, run on the same node, but on different GPUs, so that in-memory transport of the data can be achieved. And in this case, the model learns correlations using unsupervised techniques between the emitted radiation and the particle dynamics. So this is an overview of the ML architecture. It uses an invertible neural network, and it predicts particle dynamics from radiation intensities. So this is a general overview of it, and the goal is to, again, find plasma instabilities, connecting radiation with the source of the plasma. Again, this has various use cases in material science and cancer applications. And due to the nature of the simulation and streaming, the model uses continuous learning, but such continuous learning techniques run into challenges due to the rate of data that is produced. And to give you an idea of what the scale that was achieved, I want to preface this by saying that not all model architectures are as scalable as LLMs. LLMs are a recent phenomenon, and there are still many ML models that do not scale as well. And we ran into similar issues with our model, where we scaled it up to 100 nodes, or 400 AMD MI250X GPUs. And we believe the model architecture was a primary constraint for scaling further, because the communication bottlenecks at that point overwhelmed any benefit we would gain from scaling further. And but the simulation part, the pick on GPU, the plasma physics part of it, can scale up to 8,000 nodes on the system. So we know that there's further room to improve. And the chart you see on the right is showing efficiency as we scale on the ML model. The efficiency goes down primarily due to communication overhead. as PyTorch GDP does a collective all reduce to average the gradients across each instance of the model that's distributed. And efficiency here is defined as the lowest possible workload benchmarked as 100% efficient. So we take what was the smallest run, which was 8 nodes, and use that as the benchmark. So the goal of this entire ML workflow was to extract physics insights from such application. The model learns correlations from the radiation predictions and also correctly identifies the instability regions. So to evaluate the performance of the trained model, the radiation spectra is inverted back to the original momentum distribution, but this remains an unsolved physics problem. So what we see is that it seems like the model learned a fundamental aspect of special relativity, which is the Doppler effect, since it reproduces the correct cutoff frequency, which you see in the gray in chart A on top, when predicting radiation spectra. But the momentum prediction was less accurate. Despite that, the model clearly identified the instability regions. So what was the point of this entire workflow? It's to prove that it's possible to learn correlations from physics simulations in real time. And this has an added benefit, and the main benefit here is that even in heterogeneous systems, they can benefit from codes like this by circumventing disk capacity and bandwidth constraints that are posed. Again, this was a large team effort, so I want to thank everyone, and I want to thank the PyTorch community and AMD for all the support to make this project happen. And I'll take any questions if you have any questions. No time for questions. Thank you. Yeah.